It's Terry Dennery of the MathWorks. So in this video, we're going to create a model reference. And those of you watching this video who've been using Simulink for a while, and especially using it to generate software that will run machines, I think you know what it is, right? And that's because it's become really kind of, I call it a standard, a baseline on how you really can take a existing Simulink model with a controller and convert that controller into code that will run the real machine, right? So it's all about facilitating the process of embedded software creation, right? I'm going to use the word component as well, right? And component and system are certainly words that go together, and essentially systems are made up of components. But there's kind of this connotation of component that there is a audience of users of a component, and they all kind of use it a little bit differently, and therefore there's this idea of standardizing it so that it can kind of facilitate the many applications that it will undertake, right? And perhaps in that last kind of description of it, that I possibly alluded to the idea that you don't want a gazillion, yeah, I'll call instances of the same thing, and that everybody's using their own version. Okay, and so certainly since I've been at MathWorks, we've really valued this term, the single truth or the one truth. All right, and it means that if I am in that audience of people who are going to be using a component, that I want to know where it is and how I download my version of it, and that it gets centrally distributed to all the you know people like myself who are going to want it. All right. So anyways, one truth is absolutely kind of entering into this too. So anyways, so to facilitate this, again with the objective that ultimately gets the software produced that will be flashed to the embedded processor, we better start talking about rates. And again, we're going to bring this term discrete calculation back into this. And again, there's a little bit of this idea that discrete means fixed time step numerical integration, right? And so I'm going to go into my robot, and you'll see kind of in the lower right-hand corner where my my mouse is, it says variable time step. Well, that's kind of continuous, and ultimately what we really do in real control systems is we sample these signals. And so I'm going to double click there, type in unit delay, right? I'm going to pop that on right there. And so with regard to modeling my sensor, well, so I might get more into modeling sensors, but for right now, the main thing to make sure is true is I do have the sample rate. All right, and so I just put in our T sub S that we introduced in earlier videos, and it's already defined with the value of 1 times 10 to the minus 4, that we're doing this at 10,000 hertz. All right, now I'm going to copy this, right? So this will be a discrete controller. Everything interacting with it will be discrete signals. And we could choose a different rate for our command signal, but I don't see a good reason why to do that right now. And so I'm going to just keep that same rate. So we just set up the 2 incoming signals for our controller to be operated at 10,000 hertz. All right, and okay, so the idea of a component is also this idea that I think, especially with software, it comes to mind the idea of a function. And the idea of a function is you have a whole bunch of local variables inside that function, and they know what they are within that function, but nobody else needs to know that outside. And all that really means also, if you think of a function, is there's this kind of sequence of calculation which begins with the first lines of the code, and then you just take it, in order, and that's the operation of the calculation that will then take place. All right, and so the way of doing that, I don't know if you know this, but these are what Simulink folks would call virtual subsystems. It means that it's just kind of visually there, but how all the numbers get crunched in the order of calculation uh, is created in a way where it doesn't even acknowledge that there are boundaries with these functions. But when we choose to make it a component, we absolutely do want to acknowledge that. We call that an atomic subsystem. And so I'll treat this as an atomic subsystem, right? And this is a very subtle visual indication, but if you look real close, those lines are a little bit wider on the border of the block and a little bit, well, they're more black, for example, than that one. All right, and with that, I think we pretty much defined or we met the requirements to convert this into a model reference, right? And so now things get kind of nice because there's a nice utility for doing that. And so I'll just go to subsystems and model reference, and we will create or convert to a reference model. And this brings up this whole user interface. Okay, it's going to do a bunch of checks. It's going to use simulation. It's going to, well, we haven't done it ourselves yet, so let's do that right now. So let's hit run. And see, I almost broke one of my most important my most important rules, which is continually hit the run button. Every time you make any change at all, it may seem innocent and actually may seem cosmetic, but sometimes you get surprised. And I kind of knew this one, all right. And the changing a signal from continuous to discrete, absolutely, you're kind of messing with the fidelity of the calculation and hence the accuracy of the calculation. And of course, what we see is that it is unstable, and it means we need to go back to our controller and let's retune some of those PIDs. So I think I'll do most of this off camera, but you'll see it's three of them are still kind of set with that simple proportional gain of 10. So it's that one, and that one. So let's take care of it. So I'll just increase the gains of all these by clicking on the faster button, and very quickly we'll get to something which seems to be a very reasonable response to a step command, right? And so these numbers update, and they'll insert them right there. And for that second controller on the bicep, I believe that's that one right there, came up with this. And so again, I'll update and click on OK. And for the turntable, I'll speed it up a little bit. I'll click on faster twice. And that looks pretty responsive now. And so we'll rerun the robot. And it is no longer shaky. I'm just going to show that whole movement. Doesn't that look good? All right, so I think we're ready now. And so we'll convert it to a model reference. All right, and that all looks pretty good. Let's click convert. And so it's a pretty formal process, and it's checking all kinds of things, and it's running simulations before and after, kind of what we did informally, just to make sure that nothing is lost in the translation. So we just passed 3 of the tests. And now it's going to run the model one more time and create the new Simulink model file with essentially the referenced controller model. And so it looks like it passed the final test. And so now let's kind of look at the Simulink model. Okay, so the block itself, its appearances have changed. And so these little diagonals on the corner, that's just a visual indication that this is a block that is referencing an existing other Simulink model, and that it created that other Simulink model for us right here. All right, and because so much of it is about interfacing, that'll be my simple explanation of what's going on here, but certainly it broke out at this level. All the signals are coming in through those bus signals. And I think, of course, as you get into coding, kind of defining those data types and defining those rates will be a big piece of what the software work will be. So Anyways, but that's the reference model right there. That's what's being referenced here. And I want to do one more thing. You'll see this is fixed time step. Um, that kind of took place as we set those rates on our sensors. I'm going to do one more thing here. I think this is important. I've certainly talked to a number of software people who like this. And so I like choosing the solver no continuous states, discrete no continuous states. And I think when we did that video where we chose the discrete PIDs and we talked about the MATLAB function, all kind of meeting this requirement of discrete. Well, this is just continuation and more formalization of that. And so discrete no continuous states is, again, what I like to call what you see is what you get. Right? And so we'll click on that. That means that all the math is readily seen in the blocks that we're showing right there. So that's our model reference right there. I'm not sure I need to, but let's go ahead and save it to the discrete, no continuous states. And I'm just gonna break out the torques as defined. I want to kind of show something. So let's go scope. Well, the torques are already broken out, coming out of the bus selector right there. What I want to do is track one of the signals. And so let's run it again. And I like to zoom in on these. Again, I call it the staircase, right? And so we'll see these torques as calculated by the controller. That if you get the signal kind of representing these kind of collection of, I'll call them horizontal and vertical segments, so it kind of looks like a staircase. That's the indication that it's a good indication that it's a discrete expression of that signal. And so we have that, although the model itself is still running with a variable time step integrator. So it's a kind of unique thing with Simulink that it can kind of properly have continuous and discrete signals interacting with each other. So anyways, I think we achieved our goal pretty well. Our goal was to get to here and to have this block expressed and represented in its own model file. And that's a model reference. All right, thank you.